This next section of the notes will cover why do some substances get hot when they dissolve and others get colder? Or could we explain what you've experienced so far, that incredible release of heat when a supersaturated solution of sodium acetate comes back out of solution? So when you look at how things dissolve, it involves actually 3 steps. So delta stands for change, H stands for heat, and SOLN means solution. So we can calculate the heat of solution, whether something gets hot, exo, or cold, endothermic, if we break it into 3 separate steps. Another word for heat is enthalpy, and we express that heat in kilojoules, usually per mole of substance. If you come up with a hot heat of solution, that's going to have a negative value. Heat was released to the environment. Just like we learned, if you come up with a cold feeling solution, then heat was absorbed from the environment. That's endothermic, and its delta H will be positive. This is a good introduction to the heat unit that's coming up. So there are 3 separate steps. Remember, we have to break forces in solute and solvent so that everybody can buddy up next to each other and dissolve in each other. The first step costs you energy. The solute particles have to get away from each other, make room. The same thing happens in the second step. The solvent particles have to move away so they can make room for the solute that's going to move into the spaces between them. But when you finally form the solution, then you have an overall exothermic reaction, or I shouldn't say overall, but for that step, it will release energy. So let's look at the math here. Here's a lovely picture. Step 1. Purple balls stand for molecules or atoms of the solute. Well, they have to separate from each other. See right here how they're close packed with each other? Something's got to break, something has to drive the breaking of those intermolecular forces. So now they got some elbow room. That's the change in heat, step 1. It's endothermic. It costs energy. Step 2. The blue stand for molecules or atoms of the solvent. Same thing. These guys have to separate from each other and make a little room for the solvent to move into those nooks and crannies. So step 2 is also an endothermic process. Now what happens is the solute, the purple spheres, and the solvent, the blue spheres, move in and dissolve in each other. That releases energy. When the purple solute and the blue solvent get attracted to each other, then that releases energy. And all you have to do to decide if your reaction is going to feel hot or cold is add up the heat it took to separate solute and solvent, compare that sum to the energy released when the solution formed, and you'll know if it was endo or exothermic dissolution. So let's look at some examples here. To determine this, we're going to take a look at the breakdown that we just saw, but in graphical form. So let delta H with the 1 represent how much energy it takes to get solute particles separated from each other. Delta H number 2 that's when the solvent particles get some elbow room between themselves. And this third line going down is representing the heat released when the solution actually forms. So it's pretty easy to do. If you add the heat it takes to break forces and the heat released when new forces formed, just look at the magnitude of those lines. If I add delta H1 plus delta H2, even summing these 2 heats is much smaller than the heat released when the new solution forms. So this heavier dark red line represents that heat overall got released. You released more energy in the third step than it cost you in the first 2 steps, and feeling that container would feel hot. And you've experienced that in several labs as the years gone by. If you look at the opposite part of this reaction, or the opposite possible scenario, this third step is always an exothermic step, but now if I add up in this context a different dissolution, the heat required to separate solute plus the heat required to separate solvent, and compare that sum to the heat released when the solution formed, this time there's a net cost of energy. It took more energy to move particles away from each other than was released when the solution formed. This energy has to come from somewhere, and it comes from the container, from the reaction or the dissolution process takes place in a beaker. Everything from the beaker out is called the surroundings. So for the reaction or the change to find that heat, it has to get the heat from somewhere. It gets it from the warmth of the room around it. So from the beaker on out is the surroundings. The system is the dissolving that's taking place in the middle. And that's why when a human touches a container that is overall endothermic heat of dissolution, it feels cold. The energy came from the surrounding environment. Now, you will probably do some examples of exo and endothermic heats of dissolution. Magnesium sulfate, when you add it to water, gives off 91.2 kilojoules per mole of magnesium sulfate, but ammonium salts require energy to go into solution, and they're going to feel cold. Magnesium sulfate can be used in instant heat packs. You just sort of crunch the bag that they come in, and water mixes with it, gets hot. Athletes who have used instant cold packs out on the field when they got an injury have been using ammonium salts in those little bags. So we can take advantage of that heat of solution. In general, the solution will form if the overall heat of solution is exothermic. That's a driving force to go to a lower energy state. If the heat of solution is too endothermic, a solution may not form. Now there's another factor determining whether solutions form, subject for another chapter. We'll come back to that. But the rule of thumb is that polar solvents dissolve polar solutes. A polar solvent might also be able to dissolve something that's ionic, like salt, for example, because they have charges on the solvent as well as full charges on the ionic salt. If it's a nonpolar substance you're trying to dissolve, we'll go after with a nonpolar solvent. Like dissolves like. Let's see. If you try to mix sodium chloride, though, in gasoline, you're not going to get very strong interactions because salt has plus and minus 1 charges and gasoline is nonpolar. So you're probably not going to get that salt to dissolve in the gasoline. So when you mix water with octane, you already know water has strong hydrogen bonds, water is polar, and you're going to have to break hydrogen bonds before you can get any water to go into solution in octane. And octane is nonpolar, so the result is, because they have an unfavorable heat of solution, endothermic, they don't mix. They don't make a solution. So to sum up, your heat of solution can be calculated by just looking at the independent steps to separate particles of solute and solute. Those are always endothermic steps. And compare that required energy to the energy released in the third step when the solution actually forms. Now you will do a couple of calculations, well, a couple of dissolutions to test this if your teacher so desires. Lastly, let's finish this short vodcast with a rerun of the factors that affect the rate of solution, the size of the particle, since dissolving only occurs at the surface. If you break the particles into smaller pieces, you increase the surface area and make things dissolve faster. Factor 2 we learned as agitation or stirring. You bring fresh parts of the solvent in contact with the solute, so of course stirring makes things dissolve faster. I think that arrow is supposed to be in that little blank. And number 3, if you already have, say, a salt water solution and you try to dissolve more salt into that, then the rate of dissolving is going to be less compared to if you had pure fresh water. So you can set 2 containers side by side, pure water, salty water, and try to dissolve some more salt into each of those. The pure water will allow the rate of dissolving to be faster because there's no solute in it at the moment. But the already existing salt solution will have a slower rate of dissolution. I think you can fill these in. Most solids, if you increase the temperature, you increase the rate of solution. For gases, however, increasing the temperature decreases the rate of solution. If anything, it makes things come out of solution, drives the gases out of the liquid in which they might be dissolved. We'll stop there, as you've already covered concentrations in another podcast.